Hello everybody. Today we will be discussing a few problems based on Castigliano's first theorem. So to have a brief look at what it says, just for the sake of it, if you consider a system and a few forces are acting on it, so it will produce a certain amount of strain energy because the system is elastic. That strain energy will be stored and the strain energy is denoted by capital U. So this strain energy, if you differentiate it with respect to the force applied, we will get the deflection, and with respect to the moment at that point we get the slope. So now the basic formula which we would be using is here. This is the formula we'll be using to find out the deflection. So the thing is, at the point where you want to find the deflection, you should have a load, and if in case the load is not provided in the system, you have to assume an imaginary load and then equate the imaginary load to zero. Let's have a look at this sum. So it wants the central deflection and the slope at the ends. The deflection at the center and slope at the ends of a simply supported beam carrying a UDL at W per unit length over the whole span. Now this is the system, and as we can see it has an UDL and we need the deflection at the center, but there is no force acting at the center, so we assume a frictional load W and we calculate the corresponding reactions at A and B. Now what we do is that we go back to this equation for finding out the deflection at C. If we observe it, we need to find out the moment at this x. X is any section assume from a point which is convenient, and the moment we have to differentiate it partially with respect to the force W. So we find out the moment, corresponding moment from A, so it turns out to be WL by 2 plus capital WL by 2 into x minus WX square by 2, and we differentiate it, put it back in the equation and integrate from 0 to L, which is the range of the beam over which the load acts. This will be the range of the beam will be important in later sums where we will be considering frames. For this it's simple, it's just 0 to L because L is the total length. And then in a similar way we find out the moment and then differentiate it with respect to the moment, and we find out the slope. Overall, if we look at Castigliano's theorem, we do need a good knowledge of how to find out the moment for a given beam. Then if we find it out, that's more than enough. Rest of the thing is actually done. Rest of the thing is given by this small equation which I showed you earlier. This one, you just substitute it into that equation and you get the answer. Now this one was an easy one. Next, if we consider an overhanging beam, the question wants the deflection and rotation of the overhanging end A. Now if we'll have a look, they have already provided a moment at the end A. So we do not need to assume a fictional moment in this case, and using the moment we find out the reactions at B and C. The only one thing is that the moment is the only force acting in here, so it will be M by L. Usually what we do to find reaction at C is that we find the moment around B. So in that case, if this was W, we multiply W into L by 3 over here, and then RC into L. But since this is a moment, we simply keep it as it's a clockwise moment, so sign will be negative minus M, and then we proceed as earlier RC into L. This is anti-clockwise, so this sign will be positive, and we get M by L. Now the rest of the sum is the same. We differentiate with respect to M, we will get this loop, and then we find out the deflection at A. Now to find the deflection, you need a fictional load W, since load at A is not provided. Hence we provide a fictional load W, proceed as earlier, find out the reactions at B and C, and then differentiate partially with respect to W, substitute in the formula, and get the answer. One thing is that you gotta substitute W equal to 0 after you find out the values and substitute into the main equation, because that load W doesn't exist. Let's have a look at the next sum. This sum is slightly different in respect that the beam's moment of inertia varies from I to minus 1.5 I in the middle to and then back to I at the end. Now when we consider a distance x, we need to find out what the moment of inertia is at that point. Till now we didn't worry about I in the equation because it was constant, but now since it varies, we do need to find out the variance at that point. So if you will have a look, there is a rectangle above and there is a triangle below. Now just ignoring the rectangle, if we consider the triangle, what we can see is there are two triangles, one at A to X, and then from A to C. So we have two triangles, so we can use similar triangles property. Here uh, the length we know to be L by 2, and the part here, so at the end it's I, in the middle it's 1.5 I. So if we consider only the triangle alone, the height will come out to be 0.5 I. Now we use the similar triangles and get the value at any point x to be this, which is I by 2 into 2 by L into x. And then since there is already an I constant in the rectangle above, we add an I here, and we get equation, or rather a formula for I at any point x. And then the rest of the matter is same. Here we do not need to assume fictional load because there's an load already provided in the question, and then we proceed as earlier. Then this sum is a bit too advanced to be asked at this stage. Let's come to this 12.5. Now this is what is called a frame. This type of frame you might not have encountered till now. This is why Castigliano's theorem comes handy. because it states that wherever we apply the load, the corresponding deflection and slope can be found out produced due to that load. So let's see what they're asking. A vertical load W is applied to the cantilever frame, and then given that EI, so the moment is constant throughout the frame, determine horizontal and vertical displacement of C. Neglect axial deformation. What this actually means is that due to this load, a torsion will be produced here, due to which deformation may take place. That's what they are telling to neglect. We won't worry about this because in most cases it won't be asked. Just for you to know, I said it. Next, let's see. W is acting vertically and B is acting. There is no P actually, but since they asked horizontal displacements at point C, we have to apply an imaginary load P horizontal at the point C. Then, as before, we write down this equation first as a starting point, and now we see that it consists of two different parts, BC and BA. Now we have to find out the individual moments for BC, apply this equation to BC, and then back to BA, and then add both. We'll get the total vertical deflection at the point C. When coming to this problem, finding out moment is critical. You may get confused when you consider BA. BC is actually simple, so if we measure x from C, it turns to be minus wx because it's a clockwise movement, and there is the reaction at A will not be considered because both are in the same direction. But for BA, when we measure, now if we consider this as a separate number, we will see that there is a moment at B which is due to this force W. Now, since these two are perpendicular, we know that W into L by 2 is the moment. This moment exists at B, but A is actually uh, rigid, so it's fixed into the ground, so there won't be any moment at A. It will be carried out through the frame, and this moment will be constant throughout AB. So this is the only change in this sum. Now, when we consider horizontal moments, you need to think a bit. If you consider P is along BC, so there won't be any moment produced due to P along BC, but P is perpendicular to AB. Now let's see how it changes. So as we see, for BC, this part there is no moment here, but for BA it's actually minus WL by 2 minus PX out. Now WL by 2 is produced here due to this weight, due to this load W, and then P again acts in a different direction, so it's P into the perpendicular direction, perpendicular distance. So we measure x from B. X is the perpendicular distance. We measure it from B for convenience. If we do it from A, it will be L minus x. So better take it from B. It will be x and much more simpler. We get it as minus WL by 2 minus PX. Differentiate it. We get minus x. and then put it back to the formula and add both, we'll get the deflection, the horizontal deflection. Again, if you remember, P is a fictitious load, it doesn't actually exist, so put P equal to 0. That's what they've done here. And then if you look at this sum, the only change is that the inertia will change. So this is actually a bending moment diagram for this beam. Just for the sake of understanding, they have given it. So only in this part Ix there will be a change. We have to calculate I actually for AB, AC and CD. So we calculate I and put it in the formula. The rest is the same. They have asked for the vertical displacement of point A. Now at point A we already have a weight W. Now due to this W, there will be a moment produced at BWA as shown in the figure, and this WA will persist through this rigid joint and then back to the support. It should decrease because at support there will be no moments. So correspondingly we can calculate the reaction at this the moment at the support. So it turns out to be W into 2.5 A minus A, and then multiply both, we get 3 by 2 WA, and then proceed as before. Just remember to find out I separately, substitute in the equation and you will get the answer.